Hi everyone, welcome back to the second part in our final assessment review lecture. So now we're going to focus more on a few Python problems, and we're going to take a step back to phase one and a little bit of phase three of the course. So we're going to start off with a problem that you saw already in your exercises. So the lowest common ancestor. You remember if you did the exercises that one of the problems was to find out what is the lowest common ancestor of two given nodes in an arbitrary binary tree that had parent attributes. And if you remember, the general way to do it was to just start at both of the nodes, keep going up until you found, um, basically find the depth of each of the nodes, compute the difference between the two depths, and then using that information, you would know exactly how many nodes to go up from each of those two nodes until you were guaranteed to find a parent. So, um, let's suppose you had node 60 here, node 90. You know that the difference between their depths is 1. So what you could do is you could go to the deeper one, like 90, go up 1, and then you just keep on going up for both of them until you find a common node. So that's great, and that could take, O of h time. But a possibly faster way to do it is if you know that the tree is actually a binary search tree. So a binary search tree is ordered. You can actually take advantage of the fact that one node is always going to be smaller than the other. And in particular, with the lowest common ancestor, um, what the ancestor is always going to have a value that is between um, both of the two nodes that you're trying to find the LCA of. So for example, with 65 and 90, what you can do is first off note that, well, the root is definitely going to be a common ancestor, but not necessarily the lowest one. If both of these nodes have a value that is larger than this node here, then you know that the lowest common ancestor should be somewhere to the right. Okay, um, because if all of these guys are larger, then and you know that the lowest common ancestor, it should be a node that is between those two nodes, then well you got to go to the right. So you would go to the right, then you would notice that 70 is actually between 65 and 90 in this case, so therefore it must be a lowest common ancestor. Okay, so let's see how to program that. And I'm going to make use of the binary tree exercises that we had before. So you remember from the exercises for week one, I gave you a bunch of exercises with binary trees, and I'm just going to make use of the AVL class and also the node class that I defined for you guys. So let's make use of from binary underscore trees underscore exercises underscore solutions import, and I'm going to make use of this AVL modified class that I had you guys do in one of the exercises, but I'm not going to make use of the k factor at all. I'm just going to make use of the root. And for node, I'm only going to make use of the data, the left and the right. So really just the vanilla BST. Going to import AVL underscore modified and also the node. Let's make our lowest ancestor BST with and I'm going to take in, let's say the root of the tree I'm going to check the ancestors of, and um, two nodes specifying, the nodes I want the LCA of. And first thing I'm going to do is I'm going to make sure that one node is smaller than the other node. Because if I can know that, if I can assume that this node is smaller than this node, then I know that I should be comparing 70 to be larger than this node 1 and smaller than this node 2 here. So I'm going to enforce that by just saying if n1's data is not smaller, so it's larger than n2.data, well, you know what? Just swap them. n1, n2 equals n2, n1. Okay? Now that I've done that, all I got to do is keep on iterating, keep on going down the tree accordingly until I find the LCA. So I'm going to go for the negation of for when I have found the LCA. If I ever don't find the LCA, that means that either my current root data is smaller than n1 or my current root is larger than n2. Why is that? Well, because I assume that n1 is smaller than n2, so if root is smaller than n1, then it must also be smaller than n2. And similarly, if root is larger than n2, it must be also larger than n1. So this case, this corresponds to the first case I have over here, where my root's 50 is smaller than both n1 and n2. Now, if that's the case, then, well, let's see, which one is it? If it's smaller than n1, smaller than n1.data, that means that both n1 and n2 are to the right of the root. And if that's the case, I'm going to go just like how I did in my example here. I went to the right. I'm going to go to the right. And if that's not true, then, well, and that means while root.data is larger than n2.data, that means that both n1 and n2 are to the left of root, which means that I need to go to the left. So if let's say these two were my two nodes, if these two are my nodes, and I note that 50 is larger than 25, then of course it must be larger than 20 as well. So the lowest common ancestor must be to the left. So after that, after I'm done, I can return the root, and that's pretty much it. So that's all the algorithm, what it entails, and now let us actually test it out. So let's set a if name equals main, and since I imported node, I'm just going to set a bunch of different nodes here. Okay, I'm going to set a bunch of different nodes. Let's just copy all this. B, C, D, E, F, G, H, I think that should be enough. So B, C, D, E, F, G, H. So set another one, I. Let's put in the values. I put 30, okay, 30, 70, 20, 60, 70, 20, and 60. I had 80, 25, 65, and 90. So that's 80, 25, 65, and 90. Okay. Let's actually make my tree. So AVL modified. AVL modified, and I'm going to set my root to A. And let's just do some inserts. So I'm going to use the AVL insert function that I set up here. So tree.avl underscore insert. I don't need to do AVL insert. I could just do a regular insert. It doesn't really matter. But anyway, so AVL insert, I can insert my B. I can do AVL insert C. And so on. E. And you know what? Just for fun, let's not be boring. Let's insert in different orders here. E and D. I can insert f a couple times. It's not going to do anything, right? Because the way I programmed it in the solution is that it's not going to have any duplicates. Gonna insert G. I can put an H and the I. And let's try to print the tree just to make sure that it actually looks like what it should. So let's do Python final. What did I call this? FAR? Oh, that's for final assessment review. Very funny, Chris. All right, Python far.py, and yeah, there you go. We have okay, so we have so I inserted, let's see, B, C, E, D, E, D, F, F, G, H, and I, and that corresponds to 50, 25, 70, 20, 30, 60, 80. These nulls just correspond to empty children. So just imagine writing this whole thing in a level order, and it should make sense to you. Then we have 65 and 90. So it doesn't really look quite like what I drew here. I didn't really get quite the order right, but if I were to select, let's say, 65 and 90, like here and here, I should get the same answer of 70. So let's see if that's going to really match. And let's do it as such. So I'm going to print the lowest ancestor BST of BST of tree.root. So I is 90, H is 65, and you know what? Let's print its data so we don't print an ugly looking node. And there you have it. So we got 70 as we expect. So we got the lowest ancestor BST, and we just followed the exact steps that we said in the sample solution, and there you go. All right, so let's do another problem. Let's try to do the problem of finding the k smallest elements. So you'll probably remember from the last in-person lecture I did, finding the kth smallest element was a variant of the quicksort algorithm. And you'll remember that one of the possible solutions that was a bit inefficient was to just find the k smallest elements and then just get the kth one. And that's a valid solution, but it did a little bit more work than you really had to do if you wanted to just find the kth smallest element. So, but this problem, I do want to find all the k smallest elements in a given array. And I'm going to take the same approach that I kind of hand waved in the lecture, but let's actually go over it. So the approach is basically to get initialize a max heap to get all the first k elements out of the array, and all we're going to do is we're going to on-queue another element and then dequeue from the heap. And we're going to keep on repeating that process. And if you think about it, that should lead to the heap having the k smallest elements, because as soon as we on-queue a k plus 1th element, we're going to dequeue the max from that. So no matter what, since we process every single element in this array, we are going to end up with the k smallest elements because we keep on getting rid of the max from the heap. And then as a last step, since we're probably going to want to return it in a nice order, we might as well just run the heap sort algorithm to get that. Okay, so I'm going to make use of the heap class that I provided for you guys, and also the solutions for the heap sort function. So I'm going to go ahead and use the max heap and heap sort in place functions that I have. And let me do that by just easily just including it, or sorry, importing it. So from heap class, I'm going to import max heap. From heap exercises underscore solutions, I'm going to import heap sort in place. Thank you, autocomplete. And let's do it. So let's do def k smallest elements of array, and I'm going to have some k. Let's set a max heap equal to, well, the max heap class that I set. We're going to go through every single element in my array, and I'm going to, first step is to onQ the element. So that's step 2. And now if I have already gotten all my k elements, that means the next element I get will be the k plus 1th element. So how about we do a quick check to see if the max heap, if its size exceeds k. And if that's the case, then I'm just going to deq from it. So I'm going to get rid of the current maximum of the array. Okay, now if I keep on doing that, I'm going to reach the end of the array, and my max heap should have all k smallest elements. So then the final step that all I have to do is just do a quick heap sort in place on my max heap. And specifically, it's going to be on the heap attribute of my max heap object. So that should do it. I can just return my newly sorted heap, and that should work out. Oh yeah, let's be a little bit organized. So let's say that this is going to test lowest common ancestor, and here I'm going to test k smallest elements. So if I were to test this out, let's just set my array equal to whatever I had here. So 1, 5, 4, 7, 8, 4, 3, 2. Okay, so 1, 5, 4, 7, 8, 4, 3, 2. Okay, just like how I did here, I'm going to set k equal to 5. And now let's just print it out. So print the k smallest elements of array and k. Let's see what we get here. And here we go. So we get 1, 2, 3, 4, 4. And if you were to look at what we got, that indeed matches what are the k smallest elements, right? So 1, 2, 3, 4, and the repeated 4. Awesome. Now another problem is called the Dutch national flag problem. So this problem arises whenever, well, hold on. So first of all, some trivia. So this was by the Dutch computer scientist Dijkstra. So remember, he's the guy who made, Dijkstra's algorithm. If you're very attentive in my C lectures in phase 2, you'll also note that he was quoted to say that go-to statements in C are evil. So try to look for that little Easter egg in my slides. And the Dutch national flag problem is basically, it's stated there, but basically given an array that may be unsorted, the whole point is to choose some pivot index, which will give you the pivot value, and just move the elements of the array around such that all the elements smaller than the pivot are to the left, all the elements equal to the pivot are follow those previous elements, and all elements larger than the pivot are after those the pivot values. And this is useful, especially if you want to make quicksort more robust. So remember how I said that quicksort can be theta of n squared if you ever have a case where you're given a sorted list or a sorted array, and you always choose the last element. Well, it's always going to do quicksort. It's going to quicksort is going to recurse on the n-1 elements every single time. But another nasty case is if you have repeated elements in your array. So imagine if you have a bunch of 5s and all your elements is basically like a 5. And even if I were to randomly choose my pivot, The way that it's going to work is that I'm still going to move all the elements less than or equal to 5 to the left of that 5, and all the elements greater than 5, which is nothing, to the right. So what's going to end up happening is that um, all the elements that are less than or equal to 5 will be to the left. So that's going to be my n minus 1 elements of my array. And what am I going to do? I'm going to call quicksort on those n minus 1 elements. So even though I randomly choose my pivot, let's say, if you have repeated entries, quicksort is still going to run on n minus 1 elements at a time, basically. And that's not cool because that basically means that the more concentrated I have duplicate entries, um, the the closer to the worst case quicksort is going to run in. Okay, so that's not cool. And the Dutch national flag problem, what that can do is, since we're partitioning the array first into smaller, equal, and larger elements, what you can do is, instead of doing the Dutch doing quicksort on the left subarray and the right subarray, according to just that one pivot value, you can actually do quicksort on all the smaller elements and then run quicksort on all the larger elements. So Dutch national flag problem basically lets you know which elements in the array those correspond to, and hence that'll avoid that issue of getting that worst case time complexity of theta n squared. All right. So Dutch national flag problem. Let's just get right to it. So just like how we did in insertion, selection, and what yeah, basically those sorting algorithms. There was an invariant that we set for those. So let's follow a similar approach in order to solve this problem. So I'm going to set three, or actually four, invariants here. Okay, and they're going to be like let's say that a from 0 to some index bottom minus 1 will only contain smaller elements, bottom to middle. And remember, I'm using Python indexing here, so 0 to bottom here basically means 0 to index bottom minus 1. So just remember that. A of bottom to middle has equal elements. Middle to top will be the elements we need to process. So I'm going to initialize middle and top just like this. So middle will be 0, top will be the length of the array. And you'll note that all of the elements from middle to top minus 1 are going to be the elements we need to process, and a of top to the end will have large elements. So basically these three guys here are basically empty, and only this guy has the entire array. So we are going to keep processing one element at a time. We're going to swap around elements accordingly, such that these invariants are met, and we're going to keep on going until we make this subarray vanish. So let's start. I'm going to denote gray to be elements we still need to process, and let's get to it. So we're going to first start and notice that a of middle is equal to the pivot. And oh yeah, by the way, I'm going to choose the pivot to be uh, according to the index of 6, which is this 3 value here. So just remember from here on out that the pivot value is 3. And the first element is equal to the pivot. So since they're equal, that just means that I can just increment my middle variable to note that this invariant of a of bottom to middle contains equal elements, right? So bottom to middle minus 1, so just this 3 is indeed equal to the pivot, and it's an equal element. Next, I'm going to look at a of middle again. I'm going to note that it's smaller than the pivot, so it's a 2. So that means the bottom index needs to be updated accordingly to hold, 0 to bottom has smaller elements. So to do that, what I'm going to do is I'm going to swap a of middle and a of bottom, like such. And now I'm going to color it blue to note that, a of 0 to bottom indeed has all the smaller elements. I'm going to increment middle as well so that I can start processing new entries that I need to process. Okay. Next, I'm going to note that the next guy, a of middle, is larger than the pivot. So that means what I would do here is I'm going to now decrement top so that I can now replace the new top index with an element that I just found to be larger than the pivot. So I'm going to decrement top, I'm going to set 1 to 7, and I'm just going to, I'm going to swap it. So this will become a 1 as such. I'm not going to increment middle because the element that's now at middle is still an unknown element because I have no idea what I just moved from all the way at the top here. So I'm going to keep middle where it is. And now A of middle is smaller than pivot, so I'm going to do the same thing I did with the 2. I'm going to swap A of middle and A of bottom to get 1 and 3. I'm going to increment bottom and middle accordingly, and I'm just going to keep on going. It's equal, so all I got to do is increment the middle. And note that note my color scheme here. I'm slowly building these invariant ranges here. The blue has all the lower ones, the whites have all the equal ones, and the reds have all the larger ones. If you know what the Dutch national flag looks like, you'll understand why I chose these colors. And keep going. A of middle is larger than the pivot, so we're going to swap after we decrement top. So 3, 7, and then we get another red element. And now we see that A of middle is equal to the pivot again, so all we got to do is increment that middle and get another white element. And now it's smaller, so just swap the middle and the bottom such that this guy gets the value that it needs, which is the 2, and this 3 just goes over here as such. And now we've reached a case where middle and top are equal to each other, so we are done. And note that the whole array is colored just like the Dutch national flag, and that was just there to really guide you in knowing when we're really done. So basically, Dutch national flag problem, the solution is to basically build a Dutch national flag, and then if you can do that, you are done the algorithm. All right. So let's go through that in code, and we're just going to do exactly what I was just saying out loud there with all those checks. So I'm going to take an array. I'm going to take a pivot index, and first of all, I'm going to find out what is my pivot. It's going to be array at the pivot index, so that happened to be 3 in my example. Okay. The next step is to actually know where am I going to initialize my bottom, middle, and top values. So here I set them to 0 for bottom and middle. I set the top to the length of the array. Okay, so let's set that. Bottom, middle, and top will be equal to 0, 0, the length of the array. And I'm going to keep on going until middle is still smaller than top, because remember when middle is equal to top, that's a stopping condition. And I can just quit out. So I'm going to do this while statement. I'm going to do while array of middle. If the array is ever smaller than the pivot, so that corresponded to this situation here, I'm going to swap A of bottom and A of middle, and then increment middle and bottom indices. I'm going to set array of bottom, array at middle, equal to array at middle, array at bottom. Okay, and I'm going to set middle, bottom equal to middle plus 1, bottom plus 1. I'm going to increment both of them. Then how about what if array at middle, if array of middle is equal to the pivot. So if that happens, then remember that's just like this case here. So all I got to do is increment the middle by 1. And then else, that happens if, that's the only other case that can happen, is if the A of middle is larger than the pivot. So that means that I'm going to set top to be decremented by 1, and then I'm going to swap A of middle and A of top equal to array at top, array at middle. Okay, and that's pretty much all I have to do. because by the time this while loop is done, then middle will be equal to top, and I will have built my Dutch national flag. So let's test it out. I'm going to test the Dutch national flag problem. Let's set some array, my array equal to whatever elements that I start with. So 327372231. So that means 327372231. Okay, so that's right. I'm going to run my Dutch national flag my function on my array. And what did I set I equal to? 6. Let's see if that actually indeed did what I wanted it to do. So I'm going to print my array. Okay. And if all goes well, it should print exactly what was the result last time. And oh no, I accidentally misspelled Dutch national flag. No big deal. And look at that. 212333377. Very nice. I believe, if I recall correctly, that is exactly what the result was. Excellent. Looking good. All right. And so just to let you guys know, so this will be the final problem that I do for the final assessment review that is on primarily covered material. I'm going to do one more problem on dynamic programming, but if you guys haven't been keeping track of the bonus lectures, don't worry about it. If you do want to understand what's going to happen in the next few minutes, make sure you watch the dynamic programming lectures that I did a few days ago. Okay, so right now I'm going to assume that you guys have watched both of those videos. In this next problem, I am going to revisit the edit distance that was presented as the last problem in the second set of slides. And if you'll notice, I did a bottom-up approach in that lecture, just because I wanted to show a relatively easy case of dynamic programming. In this problem, I'm going to do the same exact thing, except I'm going to do a memoization approach. You remember memoization is basically like the middleman between recursion and bottom-up, in that they both memoization and recursion, they use recursion, but memoization just adds a cache, which is used by the bottom-up approach. Okay, so it's kind of like almost a best of both worlds kind of story. Okay, so remember the problem is to find the smallest edit distance between two strings, and the edit is going to be defined as either an insertion, a deletion, or a substitution. And I'm just adding this use memoization thing because that's going to be part of the problem. And let's use our favorite example from going from the two anagrams, listen to silent. So this table should look familiar to you. This was the table, the cache basically that we built last time in the bottom-up approach. Again, I'm putting the first string listen on the vertical axis, the next string on the horizontal axis, and I am going to, instead of starting at the top left like I did in the DP lecture, I am now going to start at the bottom right. So because I'm going to do recursion, I'm going to attempt to find this value by recursing on its dependencies. So dependencies would be this. This guy corresponds to an insertion, this guy corresponds to a substitution, and this guy corresponds to a deletion. So it's going to be 1 plus the min of this, or if these characters are equal to each other, and only if they're equal to each other, then I just take the value to the top left of it, which would correspond to the same distance from the substring with n minus 1 characters and the other substring with let's say m minus 1 characters. So I think in the lecture I used a So it'll be A minus 1 characters to B minus 1 characters instead of A to B characters. All right, so let's go through it. And remember with memoization, to denote whether I actually need to recurse down a level, I'm going to use this -1 value to show that I do. So remember with the Fibonacci example in my first set of DP slides, the -1 corresponds to, yes, I do need to recurse. If there's any other value, I can just use that value instead of recursing on it, which is really the whole crux of memoization. Because I'm basically keeping a memo of all the different uh, values so that I don't need to repeat um, an overlapping subproblem. All right, so let's get to it. So I'm going to start off here from going from listen to silent. And to do that, I'm going to need to do a substitution. I'm going to check the substitution answer. And I'm going to, by the way, I'm going to go in the order of sub, followed by insertion, followed by deletion. Okay, so that's why I'm going to keep on recursing again, and again, and again, and again, and again. And in this case, I have now reached a base case. And by the way, I didn't mention, but you probably noticed, I initialized this array such that I have, the base cases. So you'll remember from the other DP lecture, I initialized this to 0 to 6, so the length of, so basically b plus 1, and 0 to a plus 1. So the length of the first string plus 1. And now that I've got a base case, these all have non-negative 1 values. I can just set this equal to 1 plus the min of this, which is 0 in this case. So it'll become 1. And then now I'm done with that. I go to this case and look, well, these characters are equal to each other. So all I got to do, I don't need to recurse even on the other cases. All I got to do is just copy the value of the smaller problem from L to S rather than Li to Si. So I'm just going to copy over the 1. I'm going to keep on going. Okay. And, now I'm on this case where I recurse to the insertion case. I recurse again. I'm at a base case, set that to 1 plus 1. So 1 plus this 1 is 2. And then, I just keep on repeating this process. It's not very exciting. You just keep going. Don't worry, we're going to write code that's going to do all of this for us. But I just want to review the process that's going on here. So this is set to 1 plus 1 is 2. This is, we go a recursion on the deletion option here. We notice that the characters are equal, so we don't need to do any exploration. We just need to set it equal to the top left entry. So it's going to be 2. Keep going. We have all the answers we need. 1 plus 1 is 2. We go here. 1 plus this 1 is 2. Now we go back to this case. We need to recurse on the insertion route. Recurse again, again, and now we've reached a base case. And notice how, for each of these guys, how useful it is to have these cached, because if I were to return from this and I was here, by default I would explore the deletion option as well, right? Because that's my next step. But I don't need to because it's already cached. If I try to recurse down here, I'll just immediately return this value instead of actually recursing on this this possible value of the cache, or this possible entry. So I'm going to keep on going. 1 plus 2 is 3. 1 plus 2 is 3. I'm now here. I'm now exploring the deletion cases. They're -1, so I do need to recurse on them. Recurse, recurse. I reached a base case, so it's going to be 1 plus the min, which is 2, is 3. 1 plus 2 is 3. 1 plus 2 is 3. 1 plus 2 is 3. So I'm corresponding to 1 plus these 2's here. And now I go back to this guy. I recurse. I try to go here, but hey, the E is equal to this E. So I don't need to explore at all to this realm at all. I could just copy this 3 right up to the top left. So it becomes a 3. And then now I'm back here. I'm going to explore the deletion cases. Explore, explore, explore. Reached a base case. It's going to be 1 plus 3, which is 4. 1 plus 3, 1 plus 3, 1 plus 3, and 1 plus 3 again. Finally, I've reached this guy here. I'm going to explore this element over here, and well, the n is equal to n, so that's great. I can just return whatever is this guy. So it's going to be a 3, and now I can explore the deletion cases, explore, but hey, again, the t here is equal to the t over here. So I have a very easy case. We're going to copy over the 4. So copy the 4, and now this guy is 1 plus the min of which is 4, which is 5. Now I finally have enough information to know what is the edit distance, the final edit distance between listen and silent, and that's going to be 1 plus the min of these 3 values, which will be 1 plus 3, you guessed it, equal to 4. And now we finally have the final edit distance between listen and silent. Now, what is the major difference between this and the bottom-up approach? Well, you'll note by the colors that I made with these green colors here that we did not need to make as many computations as what the bottom-up approach would do. The bottom-up approach would have started here at the top left, and it would have basically computed every single one of these until it reached the end element here. But memoization basically lets you avoid repeated computations, or not repeated computations, but unnecessary computations in order to still get your solution. So the green boxes signify where I actually had to compute, and the negative ones correspond to actually irrelevant areas of my dynamic programming problem that I actually don't need to consider to get the solution. So in that case, you can see, and I kind of alluded to this in the last, I think the last lecture on DP. Um, Basically, memoization is useful for not doing as many computations, but it can still take up more memory than the bottom-up approach because it does have that recursive um, overhead that you need to deal with. Okay, so both of them are great dynamic programming solutions. It's just that one might be better than the other depending on what you really value in that problem. Okay, so without further ado, let's code this up and wrap up this this review session. So I'm going to make an edit distance memoized, and I'm going to take 2 strings, so string 1 and string 2. And just like with the Fibonacci memoization I did, I'm going to make another function within this function. Ooh, fancy. And I'm just going to basically return what is the distance between string 1 and string 2 up to a certain index. So up to string 1 last and up to string 2 last, right? And that's going to be convenient because each of these entries corresponds to the distance between the string from, like, let's say list with an E to silent over here. That'll just be, string 1 to string 1 length minus 1 to string 2 to string 2 length minus 1. So that would be this case here. Okay, so that's going to be useful. And before I define that, let's see where I'm actually going to use it. I'm going to show where I build the cache. So first of all, let's get the actual lengths of my my strings. I'm going to set a cache variable, so it's going to be my table, and let's do something a little bit fancy with some list comprehensions. If you haven't seen it, don't worry. You can do it in the normal double for loop way, but since I'm here, I might as well just look at some fancy stuff since this is the last lecture after all. Length 2 plus 1. So this is going to correspond to the number of columns in my list of lists, and for all of those, I am going to. So sorry, -1 for underscoring range of length of 2 plus 1, and then I'm going to have, how many of those lists am I going to do? I'm going to do for underscore in range of length 1 plus 1. Okay, so length 1 corresponds to the number of rows, length 2 corresponds to the number of columns. And what did I do here? Well, when I initialized it at the very beginning of these slides here, I'm going to initialize these values. So I'm going to set cache 0, 0 equal to 0. And now I'm going to iterate through all of my elements. Let's go through all the different rows first. So these guys here, and notice I'm starting with an offset of 1 because this whole array is basically one extra row and one extra column than the length of the two strings respectively. So I'm going to go through the rows. I'm going to set the cache at row I, column 0, so the first column, equal to I. I'm going to set similarly 1 to length 2 plus 1. I'm going to set cache 0 I equal to I. Okay, so those are the columns. And what am I going to do? Well, let's return whatever this distance is between substrings. And I'm going to put as indices length 1 and length 2. So those are going to correspond to the last elements in or the last indices of each of these strings. So I know where to start at. And this is going to basically say that I'm starting at the red box here, the bottom right. So let's actually make it. And first of all, just like in the Fibonacci code, I'm going to look at the cache string 1 last. I'm going to look at the element that I'm currently on in my table. And if that's equal to -1, that means that the distance is not found yet, which means that I should recurse on this entry. So my first case is whether the two letters, so whether, remember how when I went, let's see, I'll go over here when I noted that this I is equal to this I. I'm going to check for this case first, because that's going to allow me to prevent having to recurse on lower levels, really, or on more lower levels than I need to. So I'm going to check if string 1 at string 1 last minus 1, and that's equal to string 2 at string 2 last minus 1. This corresponds to equal last characters. Then I'm going to set my cache at string 1 last, string 2 last. I'm going to set that to the distance. So now I'm going to recurse. I'm going to make sure it's equal to whatever is the distance between substrings between string 1 last minus 1 and string 2 last minus 1. So I'm going to set it equal to whatever this guy is. So yeah. All right, so that's if it's equal. The other case, sorry, I should have put a double equal sign there. Other case, I am going to compute the three values. So like over here, I'm going to compute, the substitution value, the insertion value, and the deletion value. So all three of these values I'm going to compute, which will require potentially having to recurse. So between equals -1. Hold on. Oh yeah, sorry, I was distracted by that error-looking squiggly line. Okay, so distance between substrings. Now the sub one is going to be just like the kind of like the equal case. So again, I'm going to recurse. I'm going to set that the sub distance to that. The insert distance is going to be the same thing. So it's going to be the distance between substrings are recurse, but since it's an insert that corresponds to checking the a left column, so the column to the left of it, but the same row. So if it's the column to the left of it, that means I'm going to set string 1 last to be the same, and I'm going to decrement only the string 2 last, because the string 2 last corresponds to my columns here. Which column am I on currently? And then the delete distance will be set equal to my distance between substrings, basically flipped. So this minus 1 and string 2 last. And then finally, when I have all of my values, all I got to do is set the current, my current cache value equal to 1 plus the minimum between these three options. So between the sub distance, the insert distance, and the delete distance. Now, I can, when I'm done with that, I can just return the cache at the very last element, right? Because when I'm done this recursion, I'm going to eventually end up back, well, this mini function within a function is just going to return whatever the cache should have been. And notice that if it was not equal to -1, it would have just skipped all of this recursion and just immediately returned what was in the cache. So there's the beauty of memoization here. So I know I just wrote it, but let's just test it out, because that's the best way to know if your code is functional. So let's set two strings equal to sin and silent, as I did in the example. Let's set a result equal to edit distance memoize between string 1 and string 2. Yep, so that's the same name. And let's try to print my edit distance. Okay, so I'm going to print the result, and let's see what we get. And yeah, lo and behold, it's 4, as we expect. And you know what? Let's to really make sure that we got the right table, I'm going to also return not just the distance, but also the cache itself. So let's return the cache as well in my distance memoized function. So therefore, I'm going to need to put a 0 there. And if I really want to print my cache, I'm going to do for a in result of 1, print a. That's going to be my cache. If I were to do that, there you go. So here's my cache. And if I were to look at this, I would see that it does indeed match my the final state of my cache when I finish the algorithm. You'll see that all the -1s are where they should be. -1 over there, and the -1s down here and up here. So there you have it. That is a memoization version or a memoized approach to the edit distance. All right. And remember, of course, this is all a bonus material. You're not primarily responsible for this. But hopefully you can appreciate more about the differences and the trade-offs between different dynamic programming approaches. Okay, and that pretty much does it for my lectures for ESC190. It's been a great time for me, and hopefully you guys as well. I had a lot of fun teaching you guys as a first-time instructor. Hopefully you guys enjoyed it as much as I did. And remember, if you have any questions about anything, feel free to ask on Discourse. You guys are very, very active there, which I love to see. You can also schedule a time with me via Calendly. So if you look at the online transition page, we have a link to that. You can also just send me an email if you feel that it would be more efficient to just send a question over there. But of course, I do try to ask on discourse first because discourse is where the whole class can also benefit from your questions. And yeah, um, any questions on this lecture you can ask in the comments below or on discourse. Um, uh, I guess as some final words, I wish you the best of success on finishing off, wrapping up your very first year at university. Congratulations on getting this far, and I wish you all the best on your final assessments. Uh, yeah, I'll see you guys in the final assessment for this course. And if I don't talk to you guys anymore in like let's say office hours or in any of the review sessions we have, then I wish you all the best. I hope you guys have a great summer. Stay safe, and I hope to see some of you guys in second year. Okay, goodbye.